Hello everyone, my name is Valentin Kropov and today we will talk about essential data engineering for data scientists. And before we start, I will just give you a couple of words about myself. So I'm a senior big data solution architect, work with different databases for about 14 years, and last 4 years I spent in the big data field. I'm one of the big data consultant lead at SoftServe, where we have a team of 20 plus engineers and also spreading the big data word across the community. And one of the biggest accomplishments is Kyiv big data community, where we have more than 600 people interested in big data. So, just in a few words, what this webinar about. And the main idea of this webinar is to provide data scientists with essential required information about data engineering and to better prepare them for the real projects in the data science world, right? So we will talk about different aspects. I'm certainly not will be able to cover all of them, but this is the list of most important things which data scientists need to be aware during the implementation of the project. And before we start talking about technical stuff, I would just want to quickly go through the question of involvement on a project, because this is probably the best way to approach to these technical topics, right? And if you will take a look on the project itself, the question I always have when I start a project is who is leading the project. And the answers could be very different, because we usually have a whole bunch of people in the project, like we have project managers, product owners, tech leads, architects, and so on and so forth. And who is leading data science project, in fact, among these people? And to answer this question, we really need to take a look on the stages of the projects in the data science world. And one of the best way to describe the stages of the projects is to take a look on the CRISP-DM model, which is created specifically for data science project. And it requires like a couple of stages, from statement of work to architecture, infrastructure design, implementation, and data science modeling and data science work in itself is one of the latest steps in this process, right? And from my point of view, if you will take a look on the data science project based on these stages, this means that data science is a person who is providing the result of the work at the end of the day, right? He is using requirements, he is using infrastructure, he is using architecture of the solution being built, but in fact he is the biggest consumer and the biggest responsible person for the project. Which means that the results of the project, like will be successful or not, really depends on the data science engineer, right? But this means that this person is kind of leading the project, right? And without understanding what happens on the previous stages, this person will probably not be able to lead it really successful. And that's the idea of this webinar, to ensure that the data science engineer is aware of what happens on the previous stages, and that this person at least can control it, validate it, and make like important inputs into this process to ensure that when the work will come to the stage number 6, to the data science work, he already have all the required infrastructure and architecture in place, and it doesn't require redesign and reimplementation. In every section of this webinar, we will have a checklist at the end of each section, which will be just a quick summary of what we discussed. So for this level of involvement section, the 4 important things are: data science is a boss on the project, not project manager, not technical lead, not architect. Data science engineer or engineers are the people who should lead the project. And to be able to deliver these results, they need to have required infrastructure and architecture, and they need to influence on this infrastructure somehow. And to be able to influence, they need some argumentations, they need to understand what data engineering is, what's good, what's bad. And in this webinar, I will give you all the required information to have this argumentation. So let's go to the technical topics. The main probably challenge for everyone who design an architecture or building solution is to pick up right tools, because if you make a wrong decision on early stages, it's easy to fix, but later when you already implemented a solution, changing the tools or technology could be complicated and time consuming. So when data science project starts, I really recommend data scientists to be involved into building architecture, into picking up right tool, even if they believe it's not the part of their job or doesn't like influence the data science work itself. It is not true in most cases. So if we will take a look on the big data landscape, the number of products which exist on the market is more than 300 at the moment, and it's really tough to make this, right decision what tool to pick up in this or that case. And the other things which helps to make this decision is the set of reference architectures. So for instance, Cloudera has set of reference architectures, DataStax has a set of reference architectures for the Cassandra, and cloud providers like Amazon and Google and Microsoft has their own set of reference architectures which kind of help to navigate through the variety of tools on the market. Of course, if you need to decide for instance, what distribution of Hadoop to use, you can check out many different comparison tables and decide which is good for you and which is bad. And it really depends on requirements. So for instance, if you will compare Hortonworks, Cloudera and MapR, which are three major vendors of Hadoop, they pretty much have different approach to functionality and to the enterprise features, let's call it this way. So for instance, if you really want to have some data integration out of the box, and Hortonworks provide it, while Cloudera and MapR might not have sufficient tool set. At the same time, if you really want to have very solid file system which is highly replicated, full of enterprise features, replicated across data centers and so on and so forth, then MapR has probably one of the best file system in this field. And if you're looking for the securities, and Cloudera probably invested more than others in security with a Sentry, with Kerberos and stuff like that. So as you can see, picking up different distribution of Hadoop is not just the politic decision. It also always should have some trade-off, technical trade-offs. And data science engineers should at least know the high priority top list of differences between distribution to be able to say which one is better suits the current data science project. And even more, picking up the vendors for the Hadoop can be tough because nowadays IBM, Oracle, Amazon, and many other companies have their own distribution of Hadoop, right? And they all have different differentiators. So for instance, IBM has a great set of data science algorithms, a big R package, while Oracle has a huge number of connectors and has a big data appliance, which is a huge box, if you will. And Amazon at the same time has the cloud-based Hadoop, which is called Elastic MapReduce, and they all need to be really clear, validated, and decision should be made based on what really needs to be implemented. So one of the examples from one of the real projects we've implemented recently, the solution was to build a system which analyzes log files from almost 300 web servers, and this system is being used by three categories of people. First is operations team, which just needs to monitor the servers if there are any errors, issues in log files, and just send an alert if something happens and they need to react accordingly. The second group of people is a data science and analyst who actually take the log files, analyze what's going on with the traffic, what's the click-through analysis for it, and so on and so forth. While management is really looking to see what's the capacity of our system. Do we need to buy more servers? Do we need to increase infrastructure, and so on and so forth? So the log files are just the standard Apache weblog files plus error files, and also we used to select different operational system metrics using VMstat, IOStat, and so on. And the decision on this project was between Hortonworks and Cloudera to store data, right? And the decision was made probably a couple years ago. So this is project from like days when Apache Ambari wasn't as good as it now. Yeah, and the Cloudera manager was much better in these days. So this was a plus for Cloudera. While the second very important thing was data retrieval for specific rows, right? For the row level retrieval. And Cloudera Impala at that point provided much better performance than Hive. So decision was made to use Cloudera based on these principles. The other important things when you selecting the right tool is not only check out comparison tables, but always validate and make a proof of concept of the tools which you are going to use. And for instance, for this particular project, when we started implementing it, we didn't have all these log files in place when we were going to decide which tool to use. But what we did is we created the simulator of log files, which generated the log files pretty much in the same way as Apache web server generates them. And this helped us to validate all of these tools and come up with a really informative way of comparison tools, right? We checked what's the speed of accessing data, we checked what's the compression rate in different storage engines, and we came to conclusion to use Cloudera and Impala. Right, the other important thing in picking up tools is accurate sizing. So for instance, if you will take a look on this data flow, the log files goes from the web servers to the Flume servers and then to Elasticsearch and Cloudera. And if you will take a look on this data flow connectors, you need to really ensure that data is not stuck at any of this point, which means that there is no single point of slowness in your system. This means that you need to have sufficient amount of Flume servers to accommodate all the data coming from the Apache web service. And then at the same time, you need to ensure that your Cloudera HDFS is fast enough to occur this data. And then the same happens to Elasticsearch and so on and so forth. So we really need to ensure that all of the tools you pick up are compatible and that they can work together at the sufficient level of throw output. And as of the checklist, let's go again through the toolset selection. So a couple of very quick suggestions and real world examples. If you want the fastest random access to the data, then probably Cloudera Impala is the fastest at the moment in the Hadoop world. If you need universal and fast access to the data, then MapR file system is the state-of-the-art file system. While if you're looking for data integration out of the box, then Hortonworks is probably the best tool, because it has the LND out of the box. And again, never trust paperworks, white paper, and so on. Just make a proof of concept and ensure that it all works together, even if it requires creating some emulator of data and generating some dummy data. And always ensure that each element of the data workflow chain can accommodate data from the previous element, so there is no single point of slowness in your system. This is very, very important. Now, let's talk about the RDBMS versus NoSQL. This is one of the biggest topics these days. Many companies and projects wants to start NoSQL in their projects, while I really recommend sometimes to stay in RDBMS. So for instance, imagine that you are building a system for bank and they have highly structured, highly transactional data, which will probably require tons of ad hoc analytics, complex analytics, where NoSQL is not always the best tool to go, right? And in these cases, even if you all like Cassandra, HBase, and other very cool NoSQL databases, the biggest mistake would be to use them for the highly transactional relational data. So in these cases, RDBMS is still the case. So if you work on a data science project and one of your architects or team leads, tech leads says that he wants to use NoSQL in architecture. Just double check this table of comparison and ensure that it is really case when you need to use NoSQL, that it's not the case when RDBMS might be better than NoSQL. But it's not always like, black and white when you either need to use NoSQL or RDBMS. Sometimes you need to use both. So for example, imagine that in your project, the data which comes into the system comes with a speed of like gigabytes, tens of gigabytes and so on. And at the same time, you want to run the very advanced analytics on top of this data using some SQL queries and so on. But RDBMS system, which probably is the best tool for running ad hoc analytics and SQL queries, is not the best choice when you need to acquire data very, very fast, right? In this case, we can use some kind of hybrid architecture when data first comes into the HDFS and then it comes to the RDBMS on a nightly batch jobs for the ad hoc analysis. And if you will take a look at the checklist again, RDBMS is still a very good choice when you have a structured data, when you have moderate velocity, and you want to retain complex transaction or ad hoc queries and SQL queries. Well, NoSQL is more about simple transactions, simple queries, where you can achieve a highest velocity or volume and can support unstructured data. But again, you can combine both of these solutions to achieve better flexibility and better performance when required. For instance, acquire data in NoSQL and then transfer to RDBMS for the further analysis. And if we will take a look on the NoSQL data modeling, which is probably the biggest challenge in the big data world, and the challenge comes from the problem that people try to apply the same principles they used to apply in RDBMS to the NoSQL, and of course they fail because there is a huge difference in approach. So what's the difference between RDBMS and NoSQL? In NoSQL there are three major differences. The first one is that write operations are very cheap, and there are less transactions and they are less consistent, and that means that this allows you to achieve a great read operation speed. And there are two main rules in NoSQL to remember. The first one is that you really need to spread data across the cluster. If you have 10 nodes, 20 nodes, 100 nodes, 1000 nodes, you really want to spread the data evenly across this cluster, which will give you the biggest scalability and performance. And the second is that you need to minimize the number of partitions to read. And partition is really just a subset of data which sits on one of the servers, right? So if you're looking for, let's say, for users from city Toronto, you really want to query only one server which have all of this data and which will be able to retrieve this data very fast and send it to you by network. So this is the main two principles, which are a little bit different to the RDBMS. And let's take a look how we used to model data in RDBMS. So usually we used to create the third normal form set of tables. And this data model will probably work for most of the queries you have. Do you want to see who lives in state Texas? It's very easy to retrieve this data using this schema. If you want to see who lives at specific address, or if you want to see who lives in specific city, this schema works perfectly for all of these queries and for any other queries which you can only imagine, right? So you create the table once, you create the schema once, and then you use it for as many queries as you want. And this is the biggest difference with NoSQL, because in NoSQL we usually have as many tables as queries you have, because in NoSQL we need to achieve the great read performance, and this is the main ideas of NoSQL, right? And to be able to provide this performance, you need to spread data evenly to be able to reach out only to the data you really need. And that's why in this case, in this example, we have a separate table for query which retrieves the data for the specific state, separate table for people who live in a specific city, and the same for address, and so on and so forth. So in NoSQL, please don't save a disk space. This is not the systems which were created to save a disk space, right? In NoSQL, we always sacrifice disk space to the sake of performance, right? Always pick up the right partitioning key to ensure that data is spread like evenly according to the rules of NoSQL. And remember that there is no or almost no secondary index in NoSQL tools, only primary. So this means that you probably will have to create separate tables for separate queries, and it's perfectly fine for NoSQL. And now one of my favorite topics is deployment. Many data science engineers really don't care about how the system being deployed, how the solution being deployed, right? Because they really wants to concentrate on data model stuff. But in fact, if you will take a look on deployment is like a litmus paper for the project, and it really defines the maturity of the project. Because if you will take a look on the industry 5-10 years ago, people used to do most of the things manually, right? Installing Oracle database, installing application servers. But these days, most of the work we do is automated. So for instance, if you need to deploy a solution, you just run the chief receipt or Puppet script, and it automatically bootstrap virtual machine, provision required software, configure initial parameters, and even do a validation to ensure that it's all installed correctly. And this greatly helped to save time on like developing project. So if you will take a look on one of the researches we've made together with the Rick Kazman and Honmei Chen from the SEI Institute, we came to conclusion that the difference between manual and automated approach on the projects can be up to 90% of time saving on building additional environments like QA environments, UAT environment, stage environment, and so on. And it also not only helps to save time, but it also helps to protect you in case of failure. So imagine that your production system totally lost, right? Using manual approach, you will spend probably hours or days to restore it, while in automated approach, you just run the deployment script again. It bootstrap the new VMs, it provisioned the software, configure it, and you have the new production again. So deployment is very important. I really suggest data scientists to understand how it works and at least demand the same level of automation as I just described, right? So some of the tools which are used for the automation is Ansible, Cloud Error Director, Cloud Error Manager, Ambari, CloudBreak. While for bootstrapping, for creating virtual machine, for populating them with software, the good tool is Terraform or Vagrant or other very nice tools. So yeah, the other important thing is that, for instance, if you're building a big data system based on Hadoop, you really need to ensure that the services are spread across nodes in a cluster correctly. And data scientists might say that it's not part of our job, but it's not true in fact, because if for some instance, for some reason, the system will perform slow, you will really need to understand why. And one of the reasons could be that the service layout is wrong, and I really want data scientists at least to know the basic principles of distributing services across nodes. So for instance, if you're looking for the great performance in Spark, you really need to ensure that the Spark nodes has enough memory to run the workers, right? While if you're looking for some data locality, you need to ensure that the Spark agent sits in the same nodes as HDFS nodes, right? And so on and so forth. There is huge like researches on this topic, but at least check this out, this URL, to understand what's the best practices to like making service layout and memory allocation. So the checklist for deployment is deployment should be fully automated, always, period. This is most important for any project we do. ensure that the service layout is correct, because otherwise some of the very strange things could happen and you will probably don't even know why. And if you know what's the best practices for service layout, you will easily be able to troubleshoot these issues. And always double check that you have enough memory, because DevOps engineers and people who build infrastructure sometimes are greedy to allocate enough resources, while best practices for big data projects always recommend to have huge amount of RAM, right? Okay, let's go on. Let's talk about on-premises versus cloud deployment. So if you will take a look on-premises, which means the real hardware somewhere in your building or data center, or maybe collocated in someone's data center, this is very good way to deploy the solution when you need the highest data privacy, highest speed of access to data, and if you already, for instance, have existing hardware you want to utilize, right? Plus, you want to have the best control over resource usage, because if it's your hardware, then probably nobody else will connect to this server and not run something else apart from you, even if you don't know about it, right? While the benefits of cloud is the cost efficiency, universal access, and huge choice of application operational systems, and you don't need to spend efforts on supporting it, and of course the scalability, because you probably will not be able to buy new on-premise hardware as fast as you can get it in cloud. But again, there is a solution when you combine on-premise and cloud, which is called hybrid. For instance, you can keep non-sensitive data in cloud, while on-sensitive data like credit card information can be stored on-premises. And just to give you some example of what on-premises versus cloud means. So for instance, if you want to buy an Oracle Exadata machine, it might cost up to $1 million, right? While in Amazon, you can get pretty big, like the biggest instance for almost 50 years for the same money, right? Which means that it's really cost effective. But again, double check the requirements. If you really have requirements to keep data safe because it's sensitive, then on-premise is probably the best option for you. And the same, if you want the biggest speed of access to this data, then on-premise is probably the fastest and best solution, because copying data from cloud might be a little bit slower than copying it from on-premise box, which sits in your network. And again, hybrid is a good option if you want to mix your data in cloud and on-premise. Now let's talk about the scalability and performance, because this is greatly impacts data science work, because if you will not ensure that architecture is highly scalable and it performs on a reasonable level of SLA, then whatever you do on a data science part, whatever data models you put in place, you might not achieve results you want if it doesn't perform well, right? So let's talk about the history of clusters a little bit. So a couple years ago, maybe 5-10 years ago, there was a very popular concept when you placed different components in different clusters. So we used to have separate storage clusters, separate compute cluster, separate BI or visualization layer and clusters, which means that resources are not utilized evenly, and there is no maximum utilization of resources. While these days the most popular way of building clusters is build share clusters, when resources are shared between all of these components, and depends on the load, they are distributed between these components. So for instance, you have nightly batch jobs which put a great load on HDFS, while during the day HDFS is almost not busy, and during the day you might have bigger load on the visualization component, for instance, and this greatly helps to get maximum out of the resources and hardware or virtual machines you have. Some of the biggest names in this world are Docker containers, which allows building cluster full of different components, and this is, for instance, systems like Kubernetes or Mesos, which helps you to control these different tools, to organize the resource sharing between them, to organize repairs after failure, and so on and so forth. So just take a look on this components, and if you will take a look on the Mesos and Docker, again, it allows you to maximize utilization of the resources, while it also achieves the data locality. So imagine that both HDFS and Spark sit at the same node. Of course, data retrieval which will be much faster than if you will have to retrieve data from another cluster. And again, this could be a very good trade-off. So the checklist is that if you really want a scalable cluster and if you want to get maximum out of the resources you have, then use shared clusters. Shared cluster really likes to sit on cloud platform because of the capabilities to give you many new virtual machines in a blink of eye, right? And in most cases, scalability means performance, because if the system is scalable, you can increase the size of cluster and it will give you better performance. And the last section in this presentation would be storage. And many data scientists are really asking me question like, why do I need to worry about the storage? And I will show you an example why you really need to worry about the storage. So let's take a look on the Netflix example. So Netflix has around 25 petabytes of data, petabytes of data sits on the Amazon S3, and they read almost 10% of this data daily, and they write about 10% data daily back. This could be updated data, refined data, or a new data, whatever. But the important thing about them is that they have 350 active platform users, and most of them are data science engineers. And data science engineers in Netflix are able to use any systems they want to build their calculations to provide results which are expected from them, right? And Netflix is one of the companies which already utilize this concept that data science engineer is a boss on the project. The data science people are leading their projects. And if you will take a look on architecture of Netflix solution from 2013, you will see that all data is being stored in Amazon S3, and then you have some Hadoop layer, some tools like Peak, Hive, and so on a higher level, but the data sits on Amazon S3, and all of these different users and different systems are getting data from the same unified storage, which allows them to plug any new system here, and it will work perfectly. And let's just scroll through the time and see what happens. So in 2014, they added Presto, they added Genie, Franklin, and different tools, right? But the data is still sit in S3, so there is no change here. And again, in 2015, they added even more different tools like Druid, like Spark, but data still remains in S3 storage. And what it means? This means that decision which was made to keep data in very universal, highly compatible storage like Amazon S3 allowed them to not change the storage, because if you will have to change the storage each time you change architecture or add a new tool, new component into your infrastructure, this will be a nightmare for the 350 engineers. So the storage comparison I give you is very brief to give you understanding what's the difference and which storage to use when. So as I mentioned before, Amazon S3 is universal access very cheap, very scalable storage, which will be compatible probably with most of the software which you will try to use in the big data world. HDFS is a very nice, very scalable and quite fast file system, but it's really locked on the Hadoop ecosystem. So whatever comes out of the Hadoop ecosystem will be probably a little bit harder to use, and directly attached storage or network attached storage, so-called NAS and DAS, are quite expensive, but they provide the fastest access to the data. So if you want to really put some mission critical data or really fast algorithm sort of on data, you can probably pick up this storage. Okay, and the quick checklist for storage is that again, unified access to data, Amazon S3. Very immediate access to data is directly attached storage, network attached storage, or maybe elastic block storage from the Amazon EBS. If you choose NoSQL, you need much more space than actual data because, remember, we create different tables for different queries. And this is important to understand when you decide how much storage your solution will need. And of course, never trust papers, paperworks, white papers and so on. Always build some POC prototype on top of the solution you want to build and see if this storage is good or not for you. Because storage, as in the case with Netflix, it's in the root of the system, and changing it on later stages which will cause the huge pain for the project. Okay, and the final checklist is, remember, data science engineer is the boss on the project. You are the boss on the project, and you have a right to demand the infrastructure you need. But to be able to demand it, you need to understand the difference between different tools, what storage you need, what's the automation, what's the shared cluster, and so on and so forth. And now you know the information where to get details about all of it. And I'm sure and I hope you will be better prepared in your project to achieve it and to accomplish the great data science results on your project in future. I wish you a good day. Thank you for watching this webinar and see you soon.